Polarization is a property of a light. Newton, when he came up with the theory for light, he thought the light consists of particles. So he thought light consists of particles. But using his theory, he was able to explain reflection and refraction. But he couldn't explain refraction and interference properly. Then we got Huygens, another scientist, and he said light is like a wave. But the wave he came up with is not a, a transverse wave as we understand now, but he said it's a compressional wave. So that means it's like that. It's compressed, and that's how it's propagate. So according to him, the direction the particle moves is parallel to the direction of the wave. So this way. So that's the wave he came up with, and he was able to explain reflection, refraction, diffraction, and interference, but he couldn't explain polarization because polarization is not a property of compressed waves. And then we have got Young came along, and he was able to prove the wave property of light, and he said that it can reflect, refract, and diffract and interfere. And he also came up with a quantitative proof to did a double slit diffraction, and he proved that diffraction and interference are possible with wave. Then we have the scientist called Malus, and he was able to explain the property of polarization in light. So he was able to come up with a quantitative formula to find the intensity of the light once it goes through a polarizing filter. So when he got convinced of the polarization of light, and he also communicated that to Young, and Young also agreed that light can be polarized. And from that, they were able to change the understanding of the way how light propagates. So they came up with the idea that light is not a compressional wave, but it's a transverse wave. Transverse wave. So in transverse wave, that you have the particles change in these directions. So this is the propagation of the wave, and the particles oscillates perpendicular to the wave. So this is called the transverse wave. And the wave we looked at before, this is a compressional wave where the particles oscillate parallel to the direction of the wave. So this clearly describes what's happening with polarization. So we have got two electric fields perpendicular to each other, and they're oscillating, and it's going through a vertical polarizer. And what's happening is the horizontal component is eliminated, and we only have the vertical one. And when we go another polarizer where the axis of polarization is horizontal and the wave is completely blocked. So the question is that why do we have this two wave here? Only two, because we discussed that the in light the electric field oscillates in multiple directions. So if you take a cross sections, you have got the electric field changing in many directions, but we have got only two waves here. The reason we have got the two waves here is that if you have the light oscillating in many directions, look at them as vectors. So what we are doing is we are resolving everything into two directions, x and y directions. So all these vectors here are horizontally and vertically resolved. So at the end that we have got one vertical and one horizontal. In this second diagram, we have a polarizer here, and there's another polarizer here. So this is an light where the electric fields oscillating or changing in all directions, and we're going to send that through a polarizer where the axis of polarization is this direction. So what's doing it is just removing all the horizontal components and sending out only the vertical one. So if we say this is as the intensity of I, and this is I by 2. Why? Because this is actually equal to this. So this is same as this one, because what we're doing is we're resolving the fields in two directions, x-axis and y-axis, and this filter is removing the horizontal component and getting on the vertical component. Now, if we have a polarizer like that one, it will remove everything. But what we are doing is we're using another polarizer. We call it an analyzer, which is basically a polarizer, but we can change that in a different angle. So here the axis of polarization is theta from the vertical axis. So theta is basically the angle between the incident axis and the axis of polarization. So when this vertical component comes through this filter, you obviously know, like if the axis of polarization is vertical, it will let everything go through. And if the axis of polarization is horizontal, it will block everything. But if it is an angle, that means that angle will decide how much intensity will be there in this output. So according to Malus' law, he said the output will be I input times cos square theta. So I is equal to, in this case, I by 2 times cos square theta. So in this case, that this is the axis of the oscillation or the direction of the electric field for the light, because this has already been polarized to in the vertical axis, and it's going through another polarizer which is um, having the axis of polarization at an angle of theta. So what's happening is that what comes out of it, that will have the intensity I max cos squared theta. So we can write it down here. We can say that's I, but that comes out from here, I. So I is equal to I max cos squared theta. And that's Malus law, where we can find out the intensity of the output from the input. So, so we have input and output. So what affects the output is the angle between the axis of polarization and the incident axis. So the output will be I max cos square theta. So in this question, so we are using three polarizers. So this is a polarizer and we call this analyzer. It's a polarizer, but we can change the angles. And this is also another analyzer. So we are sending a unpolarized light. That means that we resolve them into two directions, vertical and horizontal. And the intensity is I0, I naught. And when we send it through an polarizer, that is, say for instance, a vertical axis, or you can have one axis, and what comes out of is I naught divided by 2, which we discussed before. That's IA. And then we send IA to through another analyzer where the axis of polarization is 60 degrees from the incident angle. So that means that one comes out of this using the Malus law, we find out that IB is equal to IA times cos squared theta, cos squared 60. That's the angle between the incident and also the axis of polarization. And then we send that to another analyzer where we have moved the axis by another 30 degrees. So now the axis is horizontal. So when that light goes through that one, so we are going to use the angle 30 between this incident light and the analyzer to find out the output IC. So IC is equal to IB times cos squared 30 degrees, but 30 degrees is the amount of angle between the incident and the axis. So let's write the equations for IA now. So I So IA is equal to IO by 2. So to answer the first question A, this A, what's the percentage? So that means it is 50% IO. So B, we need to know what IB is. So IB, we use the Malus law again. So the IA is going from here, and the angle between the axis and the incident is 60 degrees. So it's going to be IA times cos squared 60. So IA is IO by 2 times cos squared 60 is going to be 1/4. So it's going to be IO divided by 8, which is, we can say, 0.125 IO, or in percentage, 112.5% IO. And C, we want to know what IC is. That's an interesting one because IB is this one. And now the axis is rotated another 30 degrees. So that means the axis is 90 from the vertical direction. So, but to find the output, we need to know the angle between the incident and the axis. That's going to be 30 degree. So we are going to write using the minus 2 again. So IC is going to be IB times cos squared 30 degree. So that IB in terms of IO is IO divided by 8 times cos squared 30 is going to be 3 by 4 because root 3 by 2 is cos 30. So that's going to be 3IO divided by 32. That means that will be equal to 0.0094 IO, or you can say it's 9.4%. So now the last question is, so they're saying that we are removing this one, the first analyzer. So this is the second analyzer, it's the first analyzer. So when we remove this one, so the light going into this one is going to be the one in one direction, which is vertical, and that is 90 degrees to the axis of polarization. So they're saying the output is ID now. So if we use the Malus law again for that, so ID is going to be whatever that comes out, the new, um, say IB, but that's going to be, because we have removed that, it's IA, because the second, uh, the analyzer is removed. So what comes in IA time cos squared 90. So that means that's going to be 0. So that's quite an interesting result, because when we remove the second one, what comes out of the last one is the light has no intensity in it. So it's in a perfect scenario. When the polarizers are perfect, then in this arrangement, that the intensity of the light that comes out of is 0 when the second one is removed.